Okay. Hi, everybody. Thank you for being here, managing your Black Friday logs. So, little introduction about myself. My name is Antonio Bonuccelli, and I joined Elastic back in 2014. I work as a support engineer. I have some background in development and security information event management, and these days I focus about product supportability at Elastic. So the agenda of today's presentation, we're going to have a quick high-level view of the components of the stack. May I ask how many of you use Elasticsearch? Okay. How many Logstash? Bits? Good. Great to hear. So yeah, we're going to take a look at some of the most common login architectures. And then we're going to talk about shards, what shards are, how they work, how do you do some sizing for your cluster. And then we discuss bulk size, how do you find the optimal one. And then we're going to take a look also at distributing the load from a client perspective and some final tips on optimizing disk I/O. So the Elastic Stack, these are the basic components. You probably know, you're familiar with them. So we start from bits. That's where the journey of an event starts. So bits are an endpoint agent for event collection. So they take care of grabbing raw data, packaging into some JSON, and then push it forward into the stack. They are written in Go, so they're pretty lightweight. You can deploy them on your endpoints. The footprint is really minimal. Also, bits provides a framework of libraries that you can build on. You can build your own custom bits based on your business requirements. Logstash you can think of it as a server component. It's an event collector, but also processor. So you can define inputs there, also to grab data. It's not just through bits, but Logstash it's really good at processing data. So you can do some heavy parsing, manipulation, enrichment of your data, and that's where you can basically implement your business rules for transforming the data according to your needs. Elasticsearch is the core of the solution. It is, technically speaking, is a distributed NoSQL search engine. It's really fast. It was designed from day zero to scale, so it really gives you back answers really quickly. And the language that Elasticsearch understands is JSON, so you get JSON in and out of Elasticsearch, and you can throw all the queries that you want at it. Kibana sits at the top of the stack, and you can think of it as a UI interface for the user. So you can run your searches in Kibana, you can create visualization, your dashboard. So it's common in network operation centers to see big screens with Kibana dashboard showing what's going on in your infrastructure. Also, Kibana allows for configuration and management of your components throughout the stack. So these are the open source components. It's worth mentioning XPack. XPack has basically been a set of commercial extension that we've been adding to the stack. You can get great value out of XPack. There's security, alerting, machine learning. You soon get a SQL interface. That's going to be a game changer. So Kibana traditionally has been closed source, but we recently announced at the last user conference that XPack is now going to be open. So the code of XPack will be open from next version, 6.3. It's going to be a major change for us and for our community, hopefully. So the reason for this is to allow for a simpler interaction with the community. Users are going to be able to contribute back to the features, but also the default user experience of the stack is going to be now much more rich. You're going to get, within the XPack features, you have free ones that you can use absolutely for free, like SQL interface, query profiler, Kibana canvas. There's lots of goodness there. So that's going to be a big change coming into the next release. You can check out this blog from our founder, Shai Banon, about opening XPack. There's more on that. So just to give you a full picture, we also have our own hosted cloud offering. So if you don't want to manage the infrastructure, we take care of doing that for you. It's the state-of-the-art Elastic implementation. And you can find that out at cloud.elastic.co. All the rest is just imitations. So what we did is we took that set of features and functionality and made a standalone product out of it. So you can use Elastic Cloud Enterprise to do basically to manage your own private cloud. You can install that on your premises or on your cloud provider of choice, be it Google Cloud or AWS or Azure or what have you. Another interesting thing is Elastic APM. So we're going to do also application performance monitoring. So logging architectures for a logging use case for your Black Friday. This is the minimal deployment. So we have bits sending events directly to Elasticsearch. So imagine you have your Windows domain controller. You want to grab all those events and send it for processing to Elasticsearch. You can do that. We have a lot of different type of bits. We have Linux auditing, file bits to read events. But bits also come with some out-of-the-box dashboards. So this allows you to get great value out of the box when you install bits. So bits basically will load some dashboard into Elasticsearch. For example, you can use metric bit to collect system metrics like CPU, memory, processes, all that sort of stuff, and get dashboard visualizing that data out of the box without spending time there. Logstash comes in when we want to do some processing of the data. Imagine you're grabbing your file log, you're tailing a log with file bits. However, you want to make that event more structured. You perhaps want to define some fields and have those fields with some specific value from the raw message. Or you have, for example, a field containing a source IP, and you want to enrich that information with geodata. So that's what you can do in Logstash. So it's really powerful. However, Logstash is basically in Logstash you can define input plugins, filter plugins, and output plugins. Input is what data I want to get, so bits is one of them. Filter is what to do with the data. Outputs is where to send the data. So imagine you have a HTTP endpoint, you want to grab events from there. All you need to do is define a HTTP poller input plugin in Logstash and define the frequency and what to do with that data. So likewise, for the outputs, Elasticsearch is just one of the possible destinations. Imagine you want to send some data to Amazon S3 for archiving purposes, or on some specific events, you want to send a notification to your Slack channel. That's what you can do there with Logstash. There's plenty of plugins. You're probably familiar with them. Another feature of Logstash is very important is the persistent queues. This wasn't there from day one. It's a relatively new feature. So this simplifies the architecture dramatically, meaning that in scenarios where your Elasticsearch cluster becomes unavailable, be it a network glitch or a node being overloaded and starting to reject your requests, Logstash will be able to persist that data to... Did you lose me? Anyway, I'll go ahead. Logstash will be able to persist that data into disk, so it's going to be like a buffer that you can rely on. So in that scenario where Elasticsearch becomes unavailable, there's some reliability, there is some resiliency. Logstash will be able to store that data until the destination becomes available once again. It's common to see also Kafka in large-scale deployment, especially because it's really powerful, it's really good at what it does. You can do, Kafka is a queuing system. You can do things like replication. Historically, it was a requirement before persistent queues came into Logstash. Now it can be an optional thing if you need to have that sort of functionality in its best shape. So we move to shards and cluster sizing. Some terminology for those who are not entirely familiar with it. We have this concept of cluster, the notion of cluster. One cluster is made, Elasticsearch cluster is made of one or more Elasticsearch instances. When you store data into Elastic, that goes into indices. So you can think of indices as logical grouping of data. However, if we dig further, indices are made of shards. So shards is the way to scale the data in Elasticsearch. It's the basic working unit. Each shard basically is a Lucene index, but shards do not come for free. There's some overheads, and we'll see later the implication of that. So not all shards are created equal. What does that mean? When we have an index configure with the primary shard set to 1, and we have a replication factor. So we have a primary and a replica shard. Those two make together this Twitter index. So the way that works is when we send an indexing request to Elasticsearch, to a Twitter index in this example, that request goes to the primary first, and it gets written there. And then under the hood, Elasticsearch will take care of replicating that data into the replica shard. So that basically allows for to have two copies, in this case, of the same data. When we read instead, we can leverage both primary and replica. So that gives you an idea that we can scale the read throughput by playing with the replication factor. Scaling throughput is not the only reason for having replica shards. Imagine your node containing the primary shard goes down, becomes unavailable, whatever the reason. Your operation will keep going. Elasticsearch will detect in this scenario that the primary shard is no longer available and will promote the replica to be primary. This way we can get indexing and searching going on, and our operation are not impacted. However, this is now a degraded state. We call it, we have colors to determine the state of the health of a cluster. So we say that in this case, this index went to green, from green to yellow, meaning that in yellow state, all the primary shards are assigned and allocated and started. However, the replication factor is not met. So your cluster will keep going. However, you need to be aware you lost the resiliency, the high availability there. So you can change the number of replicas at any time without impacting any operation. With the primaries, you can't do exactly the same thing. There are some technical implications behind that. However, you can change the number of primaries under some restriction. We'll see later how to do that. So we say sharding is the way to scale how the data is distributed and served. However, when you increase the number of shards, you probably also want to increase the hardware. So your data grows, you can add more nodes to your cluster, and that's how you scale the data in Elasticsearch. More data, more shards, but how many shards? We do a little discussion of shard size. It's a big topic of its own. It's not the main topic of this presentation. The answer that we say when we are asked how big the shard needs to be is that it depends. It depends on the document size, on your mappings, on the type of queries, on your hardware, of course, on the frequency of the query. It depends on many variables, and there's a lot of discussion available on how to size a shard. In this case, for your Black Friday, for a logging time-based data use case, we can assume some rule of thumbs. What we want to avoid is to end up with a gazillion small shards. When we say small, we talk about bytes, kilobytes, or megabytes. The rule of thumb is to try to end up with a shard size of about in the order of the gigabytes, and have a 30, 40 gigabyte shard as an upper limit. You want to keep in mind not just indexing and search speed, but also if a node goes down, how long does it take for Elasticsearch to copy to relocate the shard somewhere else. So that's what usually works in this sort of use case. So we do a little exercise. Imagine you have 1,000 events per second, average size kilobyte per event, and you have 3 months retention. We end up with about 7 terabytes of data. We do a little, little simplification in this presentation. The actual size of the index data will end up being bigger than the raw data. There's some metadata added during the indexing. So we have 7 terabytes of data, but that's just the primaries. So with the replication factor into account, that doubles up effectively. And also we aim here to have 10 gigabytes as the average shard size in the cluster. So how many nodes will that require? So there are several factors here, several variables. We need to set some fixed values there. We assume we have Elasticsearch instances with a 16 gigabyte heap. What we want to do is to set a fixed value, a ratio between the amount of allocated heap per node and the number of shards, so that's not unbounded. So we set that limit to 15 in this case. So we have 1432 shards divided by the number of shards that a node should have, and then we end up with about 6 data nodes. There are other scenarios, like Elasticsearch is widely used actually started mainly for text search. So think of Just Eat when you do searches there. Well, the product, the Just Eat implementation has a blog from the engineering team at Just Eat when they do searches. It's a different type of scenario, use case, or Wikipedia, for example. In that case, it's a different approach to sizing a shard. You want to set some maximum threshold for the response time. You can check that more in this. There's a webinar and a blog that go around these topics. So time-based data is the data that we have in our logging infrastructure. It's data that comes with a timestamp. Each event happen usually during that at that timestamp. So the timestamp indicates the moment that event happened. The data doesn't change in time, but also as it ages during this retention period, it kind of loses value. But also you can have, especially during your Black Friday, and spike, a consistent increase in the volume of the data. So how do we handle that in terms of indices? So the default approach a new user basically follows is to create a index for every day. The time goes by, new indexing requests come all the time. New indices gets created every day. So that's the standard way to start using Elasticsearch. So we end up with an index per day with all its shards. How do we drive behavior of index creation? Elasticsearch index templates are the feature you want to look at. So templates basically drive the way the behavior that it's followed when an index is created. In this example, for all the indices named Logstash something, we apply these rules. So these are index settings that will get applied to each index. In this case, we force the index to be created but with 2 primary shards and 1 replication factor equal to 1. We also set the refresh interval to 60 seconds. We see later what that means. Note that the default settings for primary shards is 5 primary shards. There's discussion on changing that, so that keep an eye. It's maybe something that's going to change in the future. Aliases are another feature that you want to keep in mind. It's a way to abstract the data representation in Elasticsearch, so the indices, from the application perspective. So in that, when you use aliases, you can just change these under the hood, so the application doesn't notice the change. The application only needs to know is that there's an endpoint for writing and an endpoint for reading. However, you can change the scope of these as you require the scope of your search, for example, to be. Rollover API, relatively new, is another approach, smarter, to roll over your indices. So in this case, we say an index that it's created, we define an alias. So the application, from the application perspective, this doesn't change. When I say application, I mean Logstash bits could be also your own application using our own API to write. In this case, we say when an index it's at least 7 days old, or at least 1,000 documents, or has reached 5 gigabytes in size, then we want to roll over the index. So Elasticsearch will create a new index following this template with this nomenclature. So we create logs 00002, and this is something that was introduced at some point in 5.x. So this can be automated today. You need to call that endpoint to make the rollover happen. So this can be automated today through Curator. Curator is our tool, is an external tool that plugs into Elasticsearch to perform some index curation. In the future, this will be part of a wider set of features called index lifecycle management. You will get nice UI to configure your retention, and with few clicks, you'll be sorted. So we don't want to overshard. So this is a scenario I was mentioning earlier. We start with default settings, so 5 primary shards per index, replication factor 1. We start with 3 different type of logs. It makes sense to put them into 3 different indices. So one index per day, a gigabyte of data combined across the 3 indices, and 5 shards defaults, 6 months retention, and we end up with 900 shards just for 180 gigabytes of data. So if you think about those rules of thumb that we've seen, we see that already we could have done here really with 4 or 5 primary shards. We would have been good there. So we need to recover from this gazillion shards scenario. That's what we call it. Too many shards. Each shard has overhead. You need to have some control on that. The shards do not come for free. So what we can do in this case, reindexing is one of the most loved feature. It wasn't in Elasticsearch from day 0, so it's been a big change when it came. So what we can do here, we define, the idea is basically to collapse all these indices into fewer indices. In this case, we go to 1. We define, again, a template that says all the indices named matching this expression will basically need to have just 1 primary and 1 replica. And then once we have that template, we can we can actually call the reindex endpoint. We specify what data do we want to reindex, all our gazillion shards. Where do we put it? We put it in this index. Another step that you want to do in this case is also bring your mappings in, because the reindex, with all that it does is take the value that you have stored in underscore source field, if you're familiar with Elasticsearch. So that's what you can do to collapse all these indices. Also, the reindex API can be more granular, meaning that you can point it, yes, at these indices, but only documents matching this query. So you can leverage the power of Elasticsearch DSL. So you can, in this case, we only take the data from the last month, and we reindex it here. Of course, we want to do some cleaning up. At the end of this reindexing process, we will basically end up with a new our data safely stored here, so we can get rid of all these small shards, and your cluster will be happier because we just released a lot of resources. So that's the scenario we want to, that's a starting scenario, if you like, and that's where we want to end up with. And then we are happy. Another API that you want to keep in mind is string API. This works on a per index basis. So imagine you have an index which has got too many primary shards. Remember, one of our users started with 300 primaries for his use case. It was advised so by some consultant. It was a disaster. So you want to, the string API helps there. So I said you cannot change the primaries on the fly. You need to do that under some restrictions. So the restrictions here are that you need to set the index to read only. So you need to block any write requests. And also you want to make sure that all the shards are allocated, are sitting on the same node. You don't want to run this operation over the wire. So in this example, we go from 15 primaries. Another restriction is that the target number of primaries needs to be a factor of the source number of primaries. So for example, if you have 15 primary shards here, you can shrink to 3, to 5, to 1. This is a restriction that would be lifted in the next major version of Elasticsearch, so 7.0. And we end up with a smaller indices with less shards. If you are in the opposite scenario, imagine you have you're doing monthly indices, for example. Black Friday comes, you actually you realize you have only two primaries. If you remember, we only write two primaries. What that means is, in this case, the combined write throughput of the entire cluster is limited to these two nodes. We write only two primaries. This could become a bottleneck. You can index as fast as these two nodes only are capable of. So depending on their CPU, if I see disk system, tarara. In this case, we want to invoke the split API. This is the inverse operation compared to the shrink. So that allows you basically to split the primaries. It follows similar requirements to the shrink API. So the target scenario is that we now can leverage the combined indexing power of all these four nodes instead of just two. So that's something that could be handy if you have a spike during your Black Friday. Here you can notice we have different nomenclatures. We have different type of nodes, master, data. However, that's not the scope of this presentation. So we've seen how to scale writing. What happens, the data, maybe the amount of data we have is the same, but the number of users querying the data grows. So if you remember replicas, if our user base grows, we have more users querying the data. At some point, the nodes are going to be saturated in terms of requests. In this case, we can increase the replica factor, meaning that we're going to have more copies of the same data. That's something that, of course, makes sense if you add more hardware. Same shard, if you increase the amount of shards and you don't increase the hardware, you might have contention there between more shards basically contending the resources on the same host and possibly saturating CPU or disk, and so on and so on. So bulk size is an important aspect. With such a distributed solution, we want to make sure we don't use. With such distributed solution, we want to make sure that we use the most efficient way to index. So the difference, we have different endpoint for indexing. We have bulk in single index request. So one single index request means one request, one document. When we index a large amount of documents, of data, we want to use the most efficient way, which is bulk. So one request, more documents. This is what it looks like. For example, this is a single index request. In this case, it's a put request. The body of the HTTP request is just the document. When we do bulk, we have more requests in the same HTTP payloads. Note that we have control messages that say what's the operation actually, and then we have the actual payload, which is the document or the modification. When we have, of course, a delete request, there's no payload. So when you write your own application to talk to Elasticsearch directly, you want to make sure to use that approach. It's way more efficient. So we want to determine the optimal bulk size. Which one is right? 4 per 250 documents or 2 per 500? The answer again here, like the shard sizing, is that it depends. It depends on the application, the document size, the number of nodes, the hardware, how many shards, and so on. So the best way here to go ahead is just test based on your environment. So all these variables needs to be somehow set to have a reliable test. And this is just an example. You can try basically indexing same data sets, changing the amount of documents, and you can come up with some reliable numbers. So in this case, we do a little test with using M3 instances on Amazon. The sweet spot here is probably somewhere between 3,000 and 5,000 documents per bulk request. So it's not just about, of course, the number of the documents. If each document is huge, then you, of course, will need a smaller bulk size. Distribute the load. So I was saying we have a nice distributed environment here, solution Elasticsearch. We want to make sure that we do not send all our requests into the same nodes. We want to leverage the full power of the cluster. So what we need to do is make sure we round robin the requests to avoid clogging up the same node. So we have this from the client perspective. How do we distribute the load in terms of requests? We have our own clients, so you can write directly. You don't need to use bits. If you have your own application, you might want to also use your own code, so you can use our API. We provide our own maintained API for all the major languages, and there's a huge list of community contributed APIs. Sniffing is what we want to aim for. You could technically use a fixed list of endpoints in your settings, in your client settings. So you just say, I want to send the request to these 3 Elasticsearch nodes. However, sniffing is a better approach, is smarter. The sniffing means the client will periodically poll the cluster and ask which nodes are actually available to accept requests. Imagine the scenario where one of the nodes goes down and your application is expecting that node to be available, so you send a request, but that will be timed out. So sniffing is a way to periodically have the list of the available nodes where your application can send the requests. Likewise, Logstash allows specifying an array of endpoints, but can also do sniffing. Bits today, you can just specify an array. Note that you can send bits data not just to Elasticsearch, but also to file, to Kafka, to Logstash, as we've seen before. So we took HTTP all the way in the stack. Previously, we used to have the transport protocol. It's still there. However, it's going to be probably deprecated in the long run. HTTP is the way to go. So in this case, a HTTP software hardware load balancer will also do the job. Another approach is to use coordinating nodes. So a coordinating node is a special type of instance. It's an instance that doesn't contain any data, nor it does any master job. So it's an integral part of the cluster. However, its function there is to act as a load balancer. The coordinating only node knows the cluster state. So cluster state is all this bundle of information containing the shard location, the mappings, and other settings. So in this case, coordinating nodes can do the job. It will know how to route efficiently your requests. This also is the official recommendation that we have for running Kibana, meaning that Kibana can only point to a single endpoint. So if you don't use a coordinating node, it means you need to point Kibana to one or the specific data nodes, and then that becomes could become a bottleneck. So especially keep in mind Kibana when you open a dashboard, like the date histogram, for example, that's a aggregation, of course. Aggregation can be memory intensive. So this is a way also, the best practice to also offload some of the memory pressure from the data nodes. So some final tips on disk I/O optimization. So we've seen this refresh interval parameter, so that defaults to 1 second, and that's why we call Elasticsearch a near real-time search engine. So that means that gives Elasticsearch the frequency on how often Lucene segments are created. Every time a Lucene segment is created, the data becomes available. We write segments to file system cache first. So if you increase that value, basically you relax a bit the pressure, you relieve some pressure from disks. So segments in the background, when they accumulate, they get merged. So that's a disk I/O intensive operation. The downside here is that the data becomes available for searching instead of after 1 second. Becomes available for search after 30 or 60 seconds. However, there's a gain in indexing throughput, and you provide some relief to your disks in that case. If you have some nodes that are doing mainly indexing, we know this architecture called hot worm, where we have different tiering within your cluster. So we have this indexing buffer in memory that is set by default to 10% of the total heap of each Elasticsearch instance. This is divided by default by all the active shards, where active shard is a shard that has received an indexing request at least within the last 5 seconds. So it may make sense to increase the indexing buffer. Also, a setting regarding the translog. Translog is basically a safety mechanism. So the data, when we write to segments, goes into file system cache. However, it gets written into disk through an operation called fsync only when this translog is cleared, or every X seconds. By default, we do fsync on each request. So the default settings tend to allow for resiliency and safety. If you can afford data loss, meaning if a node goes down, the translog normally is a way for Elasticsearch to recover lost operation if a node went down. By default, it's safe. It's set to a safe setting. However, if you set that value, the durability of the translog to asynchronous, basically you can have greater throughput because we do fsync to disk not on each request, but we call that fsync. The default value, once this is set to async, is every 5 seconds. So that's something that you can do if you can afford this scenario where there's power down perhaps, and those requests were not persisted to disk yet. So and that brings the presentation to an end. Just want to let you know we are hiring. Elasticsearch is an amazing company. I honestly believe that. I've been working in a lot of different places. However, I think can get better than this. We have disruptive technology. Elasticsearch is really gaining major momentum. Engineering is a core thought at Elasticsearch. We have very inclusive environments. We are working at least engineering team. You can work from anywhere you want, and so you are expected to be self-starter, proactive, not need to be micromanaged. No one likes that. And you can check our position here, and that's it. Thank you.